Okay, on to day 3, and we're going to move quickly because I don't have a ton of memory space. It says solve the following equations. Well, I want to get the exponential stuff by itself, so I'll say e to the 0.2x plus 3 equals 5. Now I can take the natural log of both sides, ln, and these should undo each other, so I get 0.2x plus 3 equals the natural log of 5. So 0.2x equals the natural log of 5 minus 3. So x equals ln of 5 minus 3 divided by 0.2, but that's divided by 1/5, which is the same as multiplying by 5. So I'll just multiply by 5. I could simplify that and get a decimal approximation if I wanted to, but I'll just leave my answer that way for now. This right here, again, I'm going to get the logarithm by itself. So that's the natural log of 3x minus 2 equals 3 by adding 5 to both sides. E to both sides, or convert to exponential form, and I get e cubed equals 3x minus 2. Now it's simply a linear equation. E cubed plus 2 equals 3x. E cubed plus 2 divided by 3 equals x, and I've solved it. Down here we've got some properties. I see the addition of two logarithms, so I think the product property, but the 1/2 is problematic. I need to move that inside as a power first. So this becomes ln x plus ln of square root 3, because that's the same as 3 to the 1/2. At which point I can make this ln of x times square root 3 using the product property. There's no property that really applies to ln 10 over ln 2. I could just leave it, or I could use the change of base and say, you know what, I'm going to write it as log base 2 of 10. That's two equally simple ways to write that. This, again, there's no property that applies to the product of two logs, only the addition of two logs, which you can then combine what's inside to become a product. But I do know that ln of e is 1, so I should be able to just write this as the natural log of 5. Coming down here, a lot of subtraction. Everything lines up, so I can simply make this log base 2 of 15 over 3 minus log base 2 of 2.5. That is log base 2 of 5 minus log base 2 of 2.5. That's log base 2 of 5 over 2.5, which is log base 2 of 2, which is 1. So this whole thing simplifies to 1. Just using the quotient property twice. Here, it looks like I could use the power property, and over here, maybe I could use the power property as well to move this inside. This becomes 50 times log of 1,000 plus log of square root 20, moving the 1/2 inside, minus log of square root 2. So this becomes 50 times log of 1,000 is 3, plus log of square root 20 over square root 2 using the quotient property. And then that simply becomes 150 plus log of square root 10, because square root 20 divided by square root 2 is square root 10. This is asking me 10 to which power is the square root of 10? That's 1/2. So this is 150 plus 1/2, or 150.5. It's possible my camera's going to die here, but we'll try and see if we can get through the next page. If ln of root a equals b, what is ln a in terms of b? Well, ln of a to the 1/2 equals b, so 1/2 times ln a equals b, so ln of a equals 2b, using some properties. And what is a in terms of b? Well, I just need to solve this for a, basically by converting it to exponential form. A should be e to the 2b. Coming down to 13, it says, in problem 9b, we consider the graph of y equals negative 4 e to the x plus 2. Find the inverse of this function and graph it on the coordinate plane given for 9b. I'm not going to graph it, but consider domain, range, and intercepts. We can swap and solve. X equals negative 4 e to the y plus 2, subtracting 2, x minus 2 equals negative 4 e to the y. Divide by negative 4, I should have x minus 2 over negative 4 equals e to the y. Now I can convert it to logarithmic form, or take the log of both sides, same thing, and I should end up with y equals the natural log of, I'll write it as -1/4 times x minus 2. If I were graphing this, I'd think, oh, this thing has been moved to the right too, and it's also been scaled, horizontally scaled by 4 and reflected. So it's kind of an interesting graph. Explain the domain and range of f of x equals x to the m over n, which depends on various combinations of m and n. So really you want to think about x to the 2/3, x to the 3/2, and maybe x to the 5/3. If you get even over even, you want to simplify. So we'll always simplify it in one of these cases. Here we've got an even exponent and odd root. So we can plug anything in. That means the domain is an element of the reals because you can take the odd root of anything. But when you raise it to an even power, you only get positive numbers, or possibly 0. Here, you can only take the even root of non-negative numbers, and when you cube those, you still get non-negative numbers. So that would be greater than or equal to 0, greater than or equal to 0. And here, you can plug in anything you want, and you can get out anything. Finally, coming down here to the bottom, how do your answers to number 14 relate to the radical and rational exponent equations such as the ones below? Solve if you dare. So x to the 2/3 equals -3. Well, x to the 2/3, y has to be greater than or equal to 0. So I can't get negatives out of this because I'm squaring these numbers. So this has no solutions. Here I get square root 3x minus 4 equals -1, or 3x minus 4 all to the 1/2 equals -1. That's odd over even, but I can only get positive numbers out, not negative numbers. I can't take a square root and end up with a negative. So again, there are no solutions to this equation. And that takes care of day 4.